Right, we are continuing with our discussion of calculus and derivatives, and I think you're going to like this section because, um, the past several sections we have been using the limit definition of the derivative, or the alternative limit definition of the derivative. And limits. And I know you guys don't like limits so much. They're the foundation for calculus, but of course, when you do the limit definition, it can be pretty tedious, pretty cumbersome. In fact, you'll notice that all of the limit definition derivatives we've done so far have been pretty straightforward functions, polynomials, a quadratic or maybe a cubic. Um, we did a radical example. We did a rational. I think we did 2 over x was one example we did. But these are pretty basic functions. We want to be able to find derivatives of all kinds of products and quotients and composite functions. And really the limit definition of the derivative just gets to be pretty impractical. So starting with this video, we're going to work through I don't know, a bunch of videos of what I call shortcut rules. That is, we're going to show how the limit definition gives us a pattern to find a derivative that works. As long as we're following the correct patterns and using the correct rules, we can basically avoid using the derivative limit definitions. Okay. Now, of course, for a test or a quiz or homework, you might be responsible for knowing the limit definitions. But going forward, I'll say this: unless I specifically request a derivative to be computed using a limit definition, you can otherwise use shortcuts. So if I don't specify to use a limit definition, then don't. Use a shortcut rule that we're going to start talking about as of now. The first one is going to be the derivative of a constant. Okay? Derivative of a constant. Now, if I ask you a question, think about a constant function. What's the graph of a constant function look like? The graph of a constant. What is it? You should know this. A graph of a constant. So let's just pick a constant. F of x equals, pick a number. It doesn't matter. 238. 238. What does the graph of that look like? Well, the graph of that looks like a horizontal line where the y value is 238. In other words, it's a horizontal line. What's the slope of a horizontal line always? No matter where the horizontal line is, slope equals 0. So there's our first shortcut rule. The derivative of f of x equals c is given by, remember this, d dx, that means the derivative of whatever's in the brackets. So the derivative of a constant function c is always 0, always. Now, you'll notice a pattern for the next several videos is that we're going to use the limit definition to show why it's true. But once we show it's true, then we can kind of forget about limit definition for this specific case. So how can we use the limit definition to show that the derivative of a constant is 0? Well, apply here the regular limit definition. So the limit, the derivative of c is going to be the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. But here's the key thing. What is f of x and what is f of x plus delta x if you're working with a constant function? If you're working with a constant function, by definition, for every input, the output is that constant, c. So whether your input is 1,000,000 or 5 or 2 1/3, whatever your input is, it doesn't matter. The output is always that constant function. That's what it means to be constant. So whether the input is x plus delta x or the input is a plain x, the output is c. So you get c minus c on the numerator, which of course c minus c is 0. 0 divided by delta, since delta x is a non-zero number, course, we're taking the limit as delta x goes to 0, but delta x is a number. It's a very, very tiny number, but it is a number. So 0 divided by that tiny number is 0. So you get the limit as delta x goes to 0 of 0. And so we have the limit of a constant function 0 now, which of course just gives us 0. Okay, so the limit of a constant function is, sorry, the derivative of a constant function is 0. Okay, super easy. This is like the easiest derivative rule of them all. That if you have a constant, its derivative is 0, because it's graphically a constant is a horizontal line. Okay, only thing you got to worry about is maybe weird constants. Okay, so here we have f of x equals 9. Okay, so clearly, f prime is 0 because 9 is a constant. If you think about the graph is a horizontal line with a y-intercept of 9. The slope everywhere is 0. Okay, here, let's use some different notation here. Let's say dx of pi. Remember, this is saying the derivative with respect to x of whatever's in the brackets. Okay, pi might, for some people, look a little weird. But remember, pi is just an irrational number. 3.14159, blah, 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 blah. It goes on forever. It's irrational. It's transcendental. But it's just a number. And if you think about the function pi, g of x equals pi, it's just a horizontal line at the y value pi. So its derivative is 0. Oh, e to the fourth. E to the fourth. Here, let's use the other derivative notation. Capital D with the subscript x. That means, take the derivative of whatever's inside the brackets. The derivative of e to the fourth. Now, e, that's the base of the natural logarithm. It's just a number. 2.718, 7168. Well, what am I thinking? Let's see. E is 2.7182. I don't know where I got the 6 from. 2.718, okay? It's a transcendental, irrational number, but it's just a number. So e to the fourth is just a number. And so, and specifically it's just a constant, so the derivative is 0. OD here. Okay, f prime. Now, we have not talked about trig at all. But what is cosine of pi? Okay, here actually I'm going to use our other notation. Let's use the d dx. Cosine of pi. But what's cosine of pi? Okay, cosine of pi is -1. Of course, so I would say cosine of pi is a constant in disguise. So even though it looks like a variable function, it's not. It's there's no x there. It's cosine of pi is equal to -1, and so its derivative is 0. Here, let's do another trig one in that sense. What about the derivative of sine of 2? Now, you might think the same thing. Like, I don't know. We haven't talked about trig. How are you going to do this? But think about it. I have no idea what sine of 2 is. 2 radians. I don't know. Let's look at a calculator real quick. Sine of 2. Sine of 2 is 0.909297 blah, 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 blah. Sine of 2. Okay. It's a constant. It's a constant in disguise, so the derivative is always going to be 0. So be on the lookout for constants, first of all, but also things that don't necessarily look like they're a constant. Here's another one. I've given this on a test before, and I've gotten wrong answers. Pi squared. Because here's the thing. We're going to have a way to differentiate power functions very soon. And so a lot of people think, oh, pi squared, that's a power function. So I'm going to do this other more complicated rule. But no, it's just a constant. Pi is 3.14159. Squared is just that number squared. It's just some number. Okay, I guess if pi is about 3, then pi squared is about 9. So it is a constant, so its derivative is 0. So always be on the lookout for those constants in disguise. Here, I'll do one more, and then one more, and then we'll wrap up for this video. What about, say, the derivative with respect to x of, I don't know, here, let's get some practice with logarithms. Well, a log base 2 of 32. Now, I'm going to be real with you. A lot of students see logarithms and freak out, and lots of students struggle with logarithms and really miss a lot of points in calculus because they don't know how to deal with logarithms. So here's a good example. Log base 2 of 32. What is it? Okay, remember, a logarithm is another way to write an exponent. So log base 2 of 32 is asking you 2 raised to what power gives you 32? It's 5. So log base 2 of 32 is 5. In other words, this is the same thing as the derivative of 5, which is clearly a constant, and so its derivative is 0. So always be on the lookout for constants in disguise. Don't lose points for a very easy question on a test because you didn't realize you were working with a constant. All right, that's the easiest rule. We're only gonna get harder from here. So in the next videos, we'll talk about how to do power functions and trig functions and logarithms and all kinds of crazy stuff. But there will be lots easier than using the limit definitions though. Okay, we'll catch you in the next video. Always feel free to ask if you have any questions.